Alright, I have time to do some more examples of angular displacement, velocity, and acceleration. So I will go through some different situations and things you might encounter. Here's a real quick one. We got a bike wheel that rotates 4.5 revolutions. How many radians has it rotated? I mean, this could be something if you're trying to find angular velocity, you need to get to radians to get there. But just remember, anytime you start talking about revolutions and radians, one revolution is a circle, one circle is 2 pi radians. And if you know those conversions, you can convert any number of revolutions into radians. 4.5 revolutions, right? One revolution is 2 pi radians. 4.5 by 2 pi, 9 pi. And we're going to take 4.5 times 2 pi. We're going to get 28.3 radians. And that's how many radians it has rotated. Alright, here's one that is a little bit useful. So you got a bird of prey, and it's looking at an object down. Now we know that this angle that it can vision is 3 times 10 to the negative 4 radians. So first off, let's put it in degrees so we can get a feel for that, what that looks like. And then how small of an object can, or how small of a mouse in this case, can our bird of prey see. So how many degrees is this? Again, same conversion as before. We know that if we have 3 times 10 to the negative 4 radians, we know that 2 pi radians are 360 degrees. So we take 3 times 10 to the negative 4, multiply by 360, divide by 2 pi, and we get an angle that's very, very small, 0.017 degree. So that's the degree that it can use to distinguish, which is pretty small. Now let's see how that applies to seeing something, okay? So let's say that the bird's 100 meters above. That will be considered our radius, okay? And we know that our arc distance, our arc length, is going to be the radius times our angle in radians. So our radius is 100 meters. And we just take that and multiply it by our radius, our radians, and it's 3 times 10 to the negative 4, and it's going to be a really, really small number. And what it's going to come out to be is approximately 3 centimeters. Okay, so what this is telling us is that 100 meters up, and this bird of prey can see a mouse that's 3 centimeters in length. That's pretty good eyesight. Alright, is a lion faster than a horse? So we got a rotating carousel, alright? Alright, and we got a child sits on a horse near the outer edge, so the horse is near the outer edge, and the lion is closer to the center, alright? And there's the center. The question A is, which child has the greatest linear velocity? Okay, so remember, linear velocity is radius, right, times our angular velocity. So when I look at this, which one has the bigger radius? Well, H does. So the horse has the bigger radius. Now let's talk about angular velocity here, part B, before we go on. What's the relationship between angular velocities? They are both like this, parallel, and this is similar to the problem in the last video. So one revolution is going to be the same for each of them in the same amount of time. So their angular velocities are going to be the same. But because the horse is farther away or has a greater radius, its linear velocity is going to be greater. So you'll feel more of the thrill of almost falling off of the merry-go-round the farther you are from the middle. So if you want a more thrilling ride on one of these carousels, that's what you want to do. Alright? So, another example here of this. So we got a carousel initially at rest. So at time is 0, it accelerates 0.060 radians per second squared. And this angular velocity will increase. The time frame is 8 seconds. At 8 seconds, we want to know the angular velocity and the linear velocity of the child, if the child is 2.5 meters from the center. So first step in A is we want to find the angular acceleration. or angular velocity of the carousel. So we can go with angular acceleration first. Angular acceleration is a final angular velocity minus initial angular velocity over change in time. Our final, we don't know our final velocity at this point, so that's what we're solving for. We're starting from rest, so initial 0, and our change in time is 8 seconds. And we know that our acceleration will make that equal to our acceleration, which is 0.060. So we're going to solve this for WF. Our final angular velocity, once we do all the math, and again, I just put this over 1 and cross multiply it. But when I get to my WF, I get it to be 0.48 radians per second. Okay, so that's my final angular velocity. So now, how does this apply to linear velocity? Okay, and that's our quick equation. Linear velocity is equal to radius times our angular acceleration, right? Or our angular velocity. And so what we do is we take our radius, which is 2.5, and we multiply it by our angular velocity, which is 0.48, to get a linear velocity of 1.2 meters per second. So that's the velocity the person feels as they're going around the carousel. So let's take a look at this same situation, and for the child here, on that same thing, what is the linear acceleration, the centripetal acceleration, and total acceleration? And this is a really good question. If we want to find linear acceleration, remember linear acceleration, right? The tangential acceleration is going to be equal to our angular acceleration times our radius. Okay. So our angular acceleration, as we figured from the previous question, right, as we know from our previous question, is 0.06. So 0.06, it's a decimal there, times our radius, which is 2.5. Our tangential acceleration is going to be 0.15 meters per second squared. B, we want to find centripetal acceleration. Acceleration centripetal, that's center secant acceleration, v squared over r. We know from our work here that our tangential velocity is 1.2. So we take 1.2 squared over our radius of 2.5, and we get a centripetal acceleration of 0.58 meters per second squared. So now we have two accelerations. We have a tangential and a centripetal. So let's draw a little picture here of this object going in a circle. All right. And I know that centripetal is this way. So I'm accelerating 0.58 meters per second inward. This way I'm accelerating tangentially 0.15 meters per second squared. To find this actual acceleration we feel, well, we got to find what it is, the total acceleration. We just make a nice right triangle and we solve for the hypotenuse. So the total acceleration that's going to be felt by our writer, our child, is going to be the square root, and it's just going to be Pythagorean theorem, of 0.15 plus 0.15 squared plus 0.58 squared. And when we do all this math, the total acceleration felt by our child is 0.60 meters per second squared. Centripetal and tangential, being that 90-degree angle, we will get a total acceleration just by adding our vectors. And we can do that making a right triangle. All right, so equations I want to show here is that anything that we do linearly with kinematics can look the same if we talk about things with angular, and with W meaning velocity, right? With theta being our distance or our displacement, that's angular displacement, and then of course angular acceleration being our acceleration. But all these equations apply, and when we start talking about, and you'll have some problems on this for the dual credit, but you'll see that this will be very, very important to be able to differentiate between angular and linear. This can make the math really, really easy on problems, and I'm going to give you an example of one. So we got a centrifuge robot, a rotor, is accelerated for 30 seconds from rest to 20,000 revolutions per minute. And the question is, what is the average angular acceleration, and how many revolutions does the centrifuge rotor turn during its acceleration period, assuming constant angular acceleration? All right. And again, constant angular acceleration means we can use these equations. So, what is the average angular acceleration? Well, obviously, angular acceleration is equal to, right, our final minus initial angular velocities over change in time. I know that my rest is my initial, so I know that WF minus 0 over my change in time of 30 seconds will give me my angular acceleration. Now, 20,000 revolutions per minute needs to be converted to radians per second before I can convert it to that, right? So I want to start going through my math here, and again, one revolution is 2 pi radians in 1 minute is 60 seconds. And work all that magic math, you get 2100, I'm rounding here, radians per second. I substitute that in for WF. I divide that by 30, and I get the angular acceleration to be 70 radians per second squared. All right. So now, solving for part B, how many revolutions has this going over, assuming constant angular acceleration? So my acceleration staying constant. And I'm going to go to this equation here to solve. I know I'm trying to find my angular displacement here. I'm trying to find how many radians I went around, which will lead me to revolutions over time. So my first step is to use this equation. Angular velocity initial times time plus 1/2 angular acceleration times time squared. Since we start from rest, that's automatically 0. So I go 1/2. I found my acceleration to be 70. And then my time was 30 seconds squared. When I math all this out, I get 31,500 radians. Again, I'm rounding to 3 sig figs here. Now I take this answer and I want to convert it to revolutions. So I just say, okay, well, radians, and I know that 2 pi radians make up 1 revolution. So my radians cancel. 31,500 divided by 2 pi gives me approximately 5,000 revolutions.